Welcome to this sailing theory tutorial. My name is Julian, and the topic of this video is true, boat, and apparent wind vectors. In this video, I'm going to present the definition of the true, boat, and apparent wind vectors, and I'm going to demonstrate how to draw wind vector diagrams for each of the main points of sail. So to start us off with this video, I want you to imagine that we have a person who's standing and they're holding a stick with a string on it. Okay? But we're going to view this person from the top down. So from the top down, this person actually probably looks something like a circle, that's their head, and the stick is there. Now because the string is kind of just flopping off to one side right now, we're not going to draw it. The only thing that we're really interested in right now is the stick and the string. I want you to imagine though that the person is standing inside their house on a windy day. So if the person stands inside their house on a windy day, again, the string is just going to flop down off the side. What happens though if the person walks around in the house? Let's say that the person is going to walk to the left. So if the person is going to walk to the left, what we would expect to see is that the string is going to stream back towards the right. Okay, similarly, if the person is going to walk up towards the door, we would expect that the string is going to stream down towards the bottom of the page. What happens if the person stands outside their door? If they're standing still, we would expect the string to blow in the wind. I want you to ask yourself what happens though when the person who's walking up the page walks out the door onto their step. What direction is the string going to blow in? And so you see that we have a motivating problem that we want to solve with vectors. And to do that, we need to make some things up first of all. So let's say that the wind is blowing at 5 kilometers per hour. And let's say that we can walk at 2 kilometers per hour. I guess the question we're asking is, what direction is the string going to blow in? So we'll start by drawing a wind velocity vector with a magnitude of 5 in the direction of the wind. I'll use these squares. 1, 2, 3, 4, 5. And for now we'll just call that V wind. Now we also know that we're walking up. And so if we're walking up, we'd be tempted to draw our velocity vector in the up direction, just like that. But remember how we reasoned that the string is going to be blowing backwards in the opposite direction of the way we're walking. And I'm going to suggest to you that if we put ourselves in the perspective of the string can't really tell the difference between walking up or wind blowing down. And so what we're going to do is we're going to represent the walking instead of with a vector for the person walking. We're going to represent it as another wind speed. So we're going to draw it as 2 squares in the down direction. And we're going to call that, I guess, also V wind. That's a bit confusing. Now, if we wanted to figure out what direction the streamer is actually going to blow in, we want to think about what's going on in this problem. And in both of the stationary cases, the streamer is blowing in the same direction as the wind vector. Right here, one direction. Right here, same direction. So let's say that we have a third case out here where we're walking with the streamer out in the wind. What we want to do is we want to find the direction that the streamer is going to blow. And it seems to me that it's going to blow in the direction of the wind vector. So we're going to take our 5 kilometer per hour wind vector and we're going to add it to our 2 kilometer per hour downwind vector. And what does it tell us? tells us that the streamer is going to blow in a direction that's combined between the wind and the walking. So in the next example, we're going to relate this back to sailing, and we're going to get a little bit more formal with the names of these vectors. So in my last example with the stick and the string, I almost confused myself by calling two vectors v wind, and then I had to make up another name, v blow, for the third vector. And that didn't sound very scientific, didn't sound very professional, and I think that we can do better. So what I want to do right now is relate it back to sailing. I'm going to draw a boat. So this is my boat sailing along with its sails trimmed. By convention, in a lot of sailing lessons, we draw our wind coming from the very top of the page. So what I'm going to suggest to you is that the wind that a person on this boat would feel, or in fact the wind that the sails would feel, is going to be some combination of wind blowing in the direction straight down the page, combined with some wind due to the motion of the sailboat, which is going to be blowing straight towards the bow of the boat. So again, we're going to want to find some answer to tell us what direction this wind is actually going to be coming from. So what we're saying is that there's going to be some other wind that we actually feel made up of these two winds. And we're going to define that formally below. So, the first definition that we need to know is the definition of the true wind. The true wind is the velocity of wind that a stationary object would perceive. So, looking back up at our diagram, that's going to be this one right here. True wind. Okay, and some examples of where we would get true wind information. Maybe a weather buoy. We could get true wind direction from a flag on shore. We could get true wind speed from somebody who's anchored or who is standing on shore, so they're not moving, and maybe they're using an anemometer. The next definition that we're going to want to learn is the definition of boat wind. So boat wind is the wind that is perceived due to the motion of the boat in the absence of the true wind. So if we were to cover up all of the other things on our diagram, the boat wind is going to be this wind over here that points straight towards the bow of the boat. So we'll call that BW, boat wind. And that leaves only one other wind vector that we need to define. So the final wind vector that we want to define is the apparent wind, and the apparent wind is defined as the vector sum of the true and boat winds. This is the wind that we actually feel while we're sailing. So we're going to go back up to the diagram one more time, and I'm going to tell you that this over here is the apparent wind. So now I think it would be a good idea to draw a true boat and apparent wind vector diagram for a boat on each of the main points of sail. And the reason why we're going to do this is because we'll see that depending on what direction the boat is pointing in relative to the wind direction, the boat wind can have either an additive effect or a subtractive effect from the apparent wind velocity. So I guess what we'll start off with is irons, and I'll just say maybe if we're towing or something like this. Okay, so just like before, we're going to define our true wind is going to be 15 knots, and it's coming straight down the page. Our boat wind, on the other hand, well, we're towing. Maybe we can tow at 5 knots upwind, so it's going to be 5 knots again. And if we're towing into irons, then our boat wind is going to be pointing straight down the page as well. And the last thing that we're going to ask ourselves is, what is the apparent wind doing? So let's start by drawing our boat. It's a short boat today. We've got our wind coming from the top of the page, like always. We're going to draw our 15 knot, so that's 5, 10, 15 true wind vector. I'm going to switch to orange and we'll draw our 5 knot boat wind vector, so that's 5 right there. So what's our apparent wind doing? Well, remember what we said, that we just need to connect our apparent wind from the tail of the true wind to the tip of the boat wind. We'll do it off to the side so that you can see all 3 arrows. And we can see then that the apparent wind, or the wind that we would perceive if we were standing in the boat, is going to be, well, it's going to be 20 knots. It's going to be 5 knots longer than the true wind, and it's going to be pointing straight downwind, so we're going to still be in irons. Okay, so is going to be 20 knots straight down. So that's irons. Next we're going to do close hauled. We have a true wind, 15 knots. We have boat wind, 5 knots. Apparent wind, and I'll draw the arrows here. So if we're sailing on a close hauled course, then our boat wind is going to be pointing down this way. And if we're sailing, well, true wind's always coming down the page. So we'll draw our wind at the top, draw our boat sailing up here on a 45-degree angle or so. We're going to start with 5, 10, 15. I'll put the arrowhead on that. Switch to orange and draw our boat wind, which is only 5. And the last thing we're going to do is we're going to connect our apparent wind just like that. So our apparent wind, and we're not going to solve for the velocity this time. We're just going to say that it's clearly going to be a little bit more than 15 knots, but it's going to certainly be less than the 20 knots that we decided on in irons. So the next point of sail I think that we're going to want to do is a beam reach, because you can sort of see that a close reach would just be a little bit more skewed off in well, it would be skewed off in this direction here. So we'll do a beam reach. So I'm going to draw my boat. I'm going to draw my wind for reference. We know that boats move a little bit faster when they're on a beam reach than they do when they're on a close hauled course. So let's say it's the same day and our true wind is still 15 knots. And it's blowing straight down the page. For the sake of argument, let's say the boat's not going that much faster, but the boat wind is maybe going to be something like 6 knots. Okay, and in this case, remember our boat is going this way, so the boat wind is going to be blowing back towards the boat from right to left. So my yellow apparent wind, what the heck's it doing? Well, what I'd like to do is landmark here off of the bow of the boat. And so remember we said we're going to be a little bit more than 5, so if this is 5, then probably to the bow of the boat is 6. So there's my 6 knots, boat wind. My true wind is 15 knots, so there's 1, there's 2, 3, so there's, oops, So there's 15 knots. Oh, that doesn't look right. Maybe that was right. So there's my true wind at 15 knots. The last thing I want to do again is connect from the tail of the true wind to the tip of the boat wind. And there is our apparent wind. So if we want to compare what's going on the beam reach to what was going on in the close hauled course, I think this is actually pretty interesting. So what I'm going to do is I'm going to copy this vector diagram and I'm going to paste it above the close hauled course, and you'll see what's going on. So what we actually have here is a situation where the true wind, see, the true wind is the same length, and we can see that there's a directional shift here in the apparent wind, where the apparent wind now appears to be coming from a little bit farther forward, or I guess you could say that it's clocked or rotated clockwise by a certain amount. So there's that. But then another thing that I think is particularly interesting is that the actual length of the apparent wind vector has shortened from close hauled to beam reach. Now this might seem a little bit counterintuitive because we always think about beam reach as our fastest point of sail, and it still is, don't worry. But the point that I want to make here is that when you're actually driving your boat on a true beam reach, which means that you're completely 90 degrees to the true wind, your boat wind is no longer really adding very much speed to the true wind vector, and your apparent wind actually gets closer to the true wind than it was when you were on close hauled. So if you're sitting on your boat, or if you're out on trap or something like that, you're actually going to feel, even though the boat's going faster, you're going to feel less wind on your face. So I think that's kind of interesting to think about. So I guess it naturally follows that we're going to do a broad reach now. So again, I'm going to draw my boat. I'm going to draw it up here this time because we're going away from the wind. The wind is still coming from the top of the page. And we're going to use the same color conventions. True wind, boat wind, apparent wind. We're going to stick with 15 knots. And on a broad reach, maybe we've slowed down a little bit. We were going pretty fast on a beam reach. Maybe we've slowed down a little bit. We're going 5 knots again. And I mean, these are really not critical numbers. So again, we're going to landmark off the bow of the boat. We're going to start by drawing our 5-knot boat wind. And next, we'll draw our 15-knot true wind. So again, that's 1, 2, 3 is 15 knots true wind. Well, look at what just happened here. The apparent wind in this case is actually significantly shorter, I would say. Significantly shorter than the true wind vector. And what that means is that the boat is actually sailing based on less wind. There's less wind velocity to push the boat around when we're sailing on a broad reach. So now what do you think is going to happen when we're sailing on a run? So we're sailing on a run, and the wind's coming from the top of the page, and we have our boat. What are we going to do? Well, same colors. Same wind speeds. Even though we would probably expect that we'd be going a little bit slower, I'm just going to stick with 5. So we're going to start by drawing our 5-knot arrow pointing straight at the bow of the boat, and that's our boat wind. Now, what's going on with the true wind? Well, we've got a problem here because the true wind actually needs to be 15 knots long. 1, 2, 3, 15 knots long, and it overlaps with the boat wind. So how are we going to draw our apparent wind? Well, we're actually just going to draw it the same way we've always been doing it. We're going to make a point here on the tail of the true wind, we're going to make a point on the tip of the boat wind, and we're going to connect those 2 points, and that'll be our apparent wind. And the result here, which is really worth noting, is that the apparent wind is shorter than the true wind by exactly 5 knots in this case. Okay, it's going to be shorter than the true wind by the boat speed. And what that means is the faster your boat travels downwind, the less wind there is to push your boat forward. And it means that your boat is going to never be able to really outrun the wind when it's sailing on a run. This concludes my sailing theory tutorial on true boat and apparent wind vectors. In my next video, I'm going to present a couple of word problems that deal with true boat and apparent wind and the implications of changes in boat speed and true wind speed on the direction of the wind that we perceive. Thanks for watching.